We're going to take a deep dive into ST Math. It's very different from other math programs, and it's well worth taking a minute to understand what those differences are, why they make the program so effective for all students, and some of the neuroscience behind the program design. So, I'm sure we've all seen these math memes. They're funny and they're all over social media, but they get at a fundamental challenge in mathematics education. I'm sure you've heard many people say, "Why can't we just teach math the way I learned it?" And given the popularity of these memes, it seems that a lot of people have this same question. What they're really asking is, how should we teach math, procedurally or conceptually? This has been a challenge in math education for a long time, and it's time to find answers. To do that, we need to change perspective. We need to ask ourselves something different. Instead of, how do we teach math? We need to ask, how do we learn math? A question from a student's point of view. About 25 years ago, a group of neuroscience researchers from the University of California, Irvine, set out to find serious answers to this question by looking at spatial temporal reasoning, its connections to music and creativity, and its connections to learning mathematics. Driving the research was the bold idea, what if math could be taught the way the brain learns? And the result of this research was the program ST Math, Spatial Temporal Math. Spatial temporal reasoning is the brain's ability to manipulate objects in space and time to solve problems. In ST Math, the problem we're always trying to solve is how to get Gigi, the penguin, across the screen. Let's see how that works in a puzzle. Notice there are no written instructions, no verbal instructions. At the start of any learning path in ST Math, everything is visual. There's no barrier to learning. Students engage by figuring it out and testing out their ideas. Let's say I'm really not sure how this works. I do see I've got 3 moves, I think, so I'll choose something I think might work and see what happens. Okay, not quite. Notice, though, I do get to try the same puzzle again, and from that immediate feedback, I think I have an idea. Let's see. And yes, Gigi makes it. So let's have a look at what's happening here from a neuroscience perspective. It's called the perception action cycle. Whenever we're tasked with solving a problem, and in this case the problem is how to get a penguin across the screen, we use our existing schema, literally neural networks, ideas we've already built. We use these to make a prediction. Here's what I think will happen. So then I take an action, in this case the moves in the game, and then Gigi takes over and animates out the consequences of my choices. Notice we get to see exactly why we got this right. So I perceive the outcome, and inside the brain, in the hippocampus, a little part right in the middle, something very remarkable happens. The prediction I made is compared to my perception. Here's what I thought would happen versus here's what's actually happened. And because I was correct, they match. And the schema that caused me to make that prediction is strengthened. Literally, chemicals flood from the hippocampus to that neural network and make it bigger and stronger. So the next time I see a similar problem, it's more likely that this schema will make my prediction. This is how we build conceptual understanding, schema like spatial reasoning, proportional reasoning, numeracy, and so on. But learning doesn't just happen when you get things right. Let's rewind and look at another possibility. Imagine a different schema fired up, causing us to make a different prediction and choose a different set of moves. The game still animates out, but this time Gigi does not get across the screen. Notice, again, I get to see precisely why I was wrong. I perceive the outcome, and in the hippocampus, my perception is compared to my prediction. But this time, they do not match. First, the hippocampus sends a signal that deprioritizes that schema. So the next time I see a problem like this, that schema is much less likely to influence my thinking. This is how misconceptions are rectified. But very importantly, a second signal is also emitted from the hippocampus, theta waves that tell the brain you need to learn something new. You need to build new schema. The work of people like Joe Bowler, the idea that students learn through their mistakes, is very accurate and based upon this fundamental neuroscience. And this is what happens in every single ST Math puzzle. And to complete a single grade level of ST Math, students will solve several thousand puzzles. That's a lot of learning by doing. And there's a reason why in mathematics, and in ST Math specifically, that we use so many visuals when we're building concepts. For most people, our visual sense is one of the fastest ways to get information into our brains during this perception action cycle. Language is a wonderful tool for enriching schema and deepening understanding when you get students to, say, explain their thinking. But language is not so efficient during this feedback process. STMath is a learning system. The feedback is immediate, visual, and continually informs students why something is right or wrong. Another challenge we have when we think about teaching versus learning is that we're very used to thinking of math as a list, like a list of chapters, a list of standards. And this is obviously useful when we're putting information in a book or deciding what order we're going to teach things in class. But this is not how the brain stores or uses mathematical ideas to solve problems. The brain would store it a little bit more like this, where each of the topics is a node, but the big difference here is that it's not just about the nodes, but about the connections between them. It's no exaggeration to say that when we talk about someone having a good conceptual understanding of math, we literally mean they have a deep schema, a rich web of connections between these ideas, and they can use them to solve very complex problems. And these connections don't happen much by accident. Students make them when we create learning experiences that are explicitly designed to build them. For example, this is a schema map of K-8 mathematics. Let's dive into one piece of this in detail, fractions, and let's see how we build the concepts and the connections. The first thing to notice here is that we never approach anything in STMath through a single model, and fractions are no exception. We have circular models, rectangular models, fractions on the number line, fractions as symbols. Students need to see how all of these ideas connect in order to build a strong schema of how fractions work. Here's a fractions question that was on the NAEP assessment a few years ago. Estimate the sum 7/8 plus 12/13. This question was also the subject of a paper in the journal Science, and that was not because kids did well. Overall in the US, only about 1/3 of 8th graders and high school seniors got this correct. The challenge here is that this looks like a question about fraction addition. Certainly every time I've ever used this in a PD or with students, everybody immediately starts doing something like this. Drawing butterfly wings, cross-multiplying, drawing a crisscross and a smile, or something. The problem here is that even if you do the correct procedure, you end up with 187 over 104, and that still doesn't look much like any of the answers, because this isn't really a question about fraction addition. It's about the concept of what a fraction actually is. If you don't understand that 7/8 is about 1, there's no way you'll get that 187 over 104 is approximately 2. Most students answered C or D, adding across the top or the bottom. What we want students to do is to visualize what these fractions mean. 7/8 is about 1. 12/13 is about 1. So if I put them together, the result will be about 2. Let's see a game that can help them do that. This is Gigi Cycle. Let's say again I have no idea what to do. I can drag this basket around. Let me put it here and see what happens. Okay, Gigi got to 1. I was wrong, but notice I get to try the same puzzle again, and this time Gigi gets to the basket. Okay, now my perception action cycle's starting to kick in. I think I have an idea about what's going on here. We're connecting these circles to the number line. So I'm going to make a prediction. I see 5 circles, and I think Gigi's going to get to 5. And yep, that seems to be working. Okay, I get it. Now, it's important to realize that we're going to see a puzzle sequence here that moves much more quickly than a student would typically see. Students would play many puzzles at each level, but we're going to see a kind of bird's eye view, or teacher's eye view, if you will, of the learning path. So, now we can ask, how far would part of a circle get? Next, this really small segment. And next we have a big change. Notice that the fraction is now given symbolically. We can no longer purely use visual reasoning to solve the problem. We're going to see shortly a game where we carefully build the connection between visual and symbolic fractions, but in this game, the student has to understand how these symbols translate. In this case, we're going to graph 1/3, now 3/4, and next we switch it up again. Notice I can no longer drag the basket. When I click it, another part of the screen lights up to indicate that I need to interact with the wheels. This is something we do continually in STmath. We ask questions one way, and then we flip it and ask them backwards. Now students need to choose how many of these wheel segments do I need to get to 2.5. 5 halves gets me to 2.5. We can ask this type of question symbolically too. How many 1/3 do I need to get just past 1? I'm graphing 4/3 on the number line. And the complexity keeps increasing. Here we have a stack of eighths. I think that should get about here. Now we can add fractions together. 1/3 plus 2/3, which is 3/3 or 1. And finally we get to questions like this, where we are estimating fraction addition on a number line. This is not about adding the fractions using a procedure. That happens in another game. But about being able to conceptually understand fractions and estimate putting them together. I know what 1/2 is, I know what 3/4 is, so I can use my existing schema and I can imagine putting them together, making a prediction, and then having it confirmed through the game through my perception action cycle. This is what schema building looks like. And of course, we can get students to the point where they can meaningfully look at a puzzle like 7/8 plus 12/13. 7/8 is a little less than 1, 12/13 is really close to 1, so together they'll be just less than 2. Really powerful. Learning through doing. This is game-based learning in action. Now, it's also very important to realize that even though STmath is a supplemental curriculum, it's also a very comprehensive curriculum. Let's take a look at 3rd grade. Here's a teacher's view of the grade level content. Notice there are 25 objectives, the typical things you'd expect to see in 3rd grade, and all standards aligned. So let's take a closer look at one of these objectives to put all this learning in context. And we'll stay with the topic of fractions. We'll look at fraction concepts. Here's a teacher view of the objective. The first thing to notice is that just to get through this one objective, a student will have to solve over 200 puzzles. And there are 25 objectives in 3rd grade, so you can do the math. That means they'll have to solve several thousand puzzles to get through the grade level. Note that every objective in STmath from 2nd grade and above has a pre and a post quiz, which a teacher can switch to English or Spanish, and these assessments are basically typical standardized test type questions. We're looking to see how well student schema building is transferring onto more typical test questions. So in this objective, there are 8 games, each of which has several levels, and every level in STmath has maybe 6 or 8 puzzles. And a student only progresses to the next level once they complete all the puzzles in a level. And here's how we adapt. If a student gets a puzzle wrong, they get to try it again. But if a student makes 2 mistakes in a level, they have to start the level again. And here's the trick. We randomly generate new puzzles every time a student comes back into that level. So they can't memorize their way through a fixed sequence of questions. They have to master the actual content in order to make progress. As students are working through the objectives, teachers can see all the students' progress and can easily see if a student is struggling too much in any one area. Notice this alert tells a teacher this student has tried a level 10 or more times. It's time to intervene. The teacher can click on the alert and see the exact level a student is on, open it, and have a conversation with the student or even a group of students, either in person or remotely, about this particular level and these puzzles. And our educator training focuses on using facilitating questions to help students figure out how to solve the problems. Teachers and students can even slow down the animation or annotate on the screen to help these conversations. Let's take a quick look at how these games build in complexity. I have screenshots here from each of the games, and you can see we start with the fundamental idea of fractions, splitting a whole into multiple parts, and that each of these parts must be equal. If students don't thoroughly have this schema, it causes all kinds of problems later on. Next, we have a game where students have to make the parts equal. Now a game where we're balancing halves and wholes. Then another balancing game, Pie Monster, where you have to make sure each of the monsters has the same fractional amounts of pies. Kids love this because when you get it correct, the monsters turn around and breathe fire, blasting the boxes out of Gigi's path. Next, we have a really important game, Match Fraction. This is one of those games I mentioned earlier where we explicitly connect visual and symbolic fractions. Notice we're given a fraction as a symbol, in this case 2/5, and we need to use this virtual manipulative to build a visual version of it. This game is also important because it clearly demonstrates what STmath is at its heart. It's a series of really well-designed virtual manipulatives wrapped inside a game-based shell with immediate formative feedback. So, as I drag this slider, it breaks the whole into an increasing number of equal parts, and we'll choose 5. Now I can drag this slider, and I'm going to choose 2 of these parts. I've built 2/5. Students will solve tons of these problems until they have a really strong fraction schema. Back to the objective. Next, we have a game where we look at fractional parts, intentionally connecting the concept of fractions to all kinds of different shapes. Then another game about converting symbols to visuals, this time with circular models. And finally, by the end of just this one objective, students should be able to look at any visual model of a fraction and describe it using symbols. Which brings us to the real power of STmath. You may be familiar with charts like this. I've seen them called Rigor Relevance charts or Quadrant D charts, and they're a useful tool for analyzing the mathematical tasks that students are asked to complete. We have an axis of thinking, kind of a Bloom's taxonomy from low-level memorization to high-level creative thinking. And here we have an axis of application, routine tasks to non-routine tasks. The idea is we want students spending a significant amount of time working on the math tasks up here, where they need to use creative and critical thinking to solve non-routine problems. But it's easier said than done. First, the vast majority of curriculum materials fall pretty squarely in the bottom left quadrant. Whether they're paper and pencil or digital, most materials don't consistently push students creatively to solve problems. And that's not to say students don't need some practice of basic math ideas. They do. But that can't be your only experience of mathematics. But for many people, especially those who are asking, why can't we teach math the way I learned it? This was their entire experience of learning mathematics, which is why the memes are so effective. But second, and perhaps the biggest problem, is that in virtually every other curriculum on the planet, the only way they have of asking a student a question in this quadrant is with a word problem, which is a barrier to entry for a large number of students. They get so lost in trying to decode the words that they never really get to tackle the underlying thinking. STmath uniquely, by initially presenting all problems visually, provides access for all students to that creative thinking and non-routine problem solving. And what's remarkable is that once you remove the language barrier, you'll be amazed at the capabilities of your students. So a great and very valid question at this point is, how does this conceptual learning methodology, based on using spatial temporal reasoning to build schema, translate into outcomes on standardized tests? And the answer is pretty awesomely. We have a lot of large-scale data studies done on the efficacy of STmath by independent organizations like WestEd and Proving Grounds at Harvard University. And I want to look just for a moment at this study, which is broken down by the effect of STmath on different student subgroups. You can see that STmath is not only highly effective for gifted students. They love it. They can move at their own pace. There are challenge puzzles which are highly intriguing. But also look at this data with the special education students. This is transformational growth. Also for English learners, all student subgroups, STmath is giving all students the chance to learn and think mathematically. It really is the cornerstone of an equity strategy, providing equitable access to learning tools proven to help all students. And students love it. It's fun. Kids love Gigi. But for the kids, this isn't about neuroscience. They don't know that it's their perception action cycle being activated, but we do hear very commonly that students understand this idea of productive struggle, of growth mindset, the idea that they are learning when they make mistakes and how powerful it is when they figure it out for themselves. And something new last year, a peer-reviewed study showed something I've never seen before when looking at ST Math or indeed anything else. This study showed that kids playing ST Math had an increased sense of self-belief towards mathematics by regularly playing a game with a penguin. It increased the amount they thought of themselves as mathematicians, which is awesome because we know from other research that students, girls in second grade, for example, are starting to see math as something not for them. But now we have a weapon to help students fight back against the misguided belief that I am not a math person. We're all math people. We just need the right tools. Which brings us back to memes. While they are funny and have a tendency to trivialize, they do strike at some important challenges in math education. For example, how should we teach multiplication? The old way or the new way? But now we can look at this question through a new lens. We can examine these different methodologies from a schema building perspective, and we'll see that they are designed to do completely different things. The old math way is a beautifully efficient algorithm that will work no matter how large the numbers are. Practicing it will build up that one node in your brain. This is a method for speed and efficiency. Now, the new math way is very different. It's actually really cumbersome, time-consuming, and not a very efficient way to multiply numbers together, hence the funny memes. But that's not what it's for. It's explicitly designed to build connections in the brain between these different mathematical ideas: place value, powers of 10, modeling situations with addition and multiplication. And for that purpose, it is really good. Now, I'm sure it's occurring to you that we probably shouldn't be teaching the old way or the new way. What we need to do, and of course what we do in ST Math, is teach both. We use area models to build the connections and conceptual understanding, and then we connect that to the efficient algorithms: speed, efficiency, and understanding. So, a good question after all of that is, how did we get here? Why is there this constant rift in mathematics education between teaching for conceptual understanding and teaching algorithms and procedures for speed and efficiency? I think the best answer could be found in this picture from the 1940s. You can see here it says computing division, computing section. What's important to realize is that the computers they're referring to in this room are not the machines. The people here are human computers, paid to be fantastically good at doing math procedures with both speed and accuracy. Within my lifetime, human computers were an integral part of getting us to the moon. But what's fascinating is this line from a 1942 memo from NASA, the National Advisory Committee for Aeronautics, which later, of course, became NASA with an S, where they say, "The volume of work often necessitates computers, as in people, who can perform the routine machine operations, as in math calculations, with great speed, but who need not have much logical insight into what the results should be." They literally needed people who could do math with speed and accuracy, but did not need conceptual understanding. And it wasn't just NASA. Banks, insurance companies, they all needed human computers. And even in the more day-to-day jobs, office manager, grocery store clerk, there was a need to be able to do math procedures quickly and accurately. It was genuinely necessary for everyday life. And this is the era during which most of our traditional textbooks were written. This is the ethos that still pervades the way we teach. But the chip in my cell phone can do more calculations in a minute than the entire room full of human computers. The old way of teaching math was to make you do it like a machine. But the new way of learning math is to help you understand how it works so that you can build the machines. There is a new currency in the world today. Employers are looking for creative thinkers to create value for their organizations and society. And what's fascinating is that researchers are consistently finding strong links between spatial reasoning and creativity, to the point that a significant number of universities across the country are finding that incoming students' performance on the PSVT, spatial reasoning assessment, is one of the best ways to determine if students are ready for the creative rigors of today's STEM courses. Yet spatial temporal reasoning is not taught explicitly anywhere in a typical K-12 curriculum. But students who've done ST Math will find this type of thing uncannily familiar. Our mission is to ensure that all students are mathematically equipped to solve the world's most challenging problems. I hope that you'll join us in helping all students have access to this remarkable schema building tool.